In this video, we're going to go deeper into determinants than we have before, looking at some of the properties. And I'll start, of course, with a theorem to get things started. So we're going to let A be a square matrix. Remember, determinants are only defined for square matrices. Let me put some numbers down here. If a multiple of one row is added to another row, to produce a matrix B, then the determinant of B is the same as the determinant of A. So multiplying a row by a number and adding it to another row does nothing to change the value of the determinant. If two rows are swapped to produce a matrix B, then the determinant of B is the negative of the determinant of A. So if you swap two rows, the determinant becomes negative. Finally, if a row is multiplied by a number alpha to produce a matrix B, then the determinant of B is alpha times the determinant of A. So if you multiply one row by some scalar, then you multiply the determinant by that same scalar. Just a row, not the whole matrix. All right, well, let's take a look at the proof of these things. Let's start. I think what we're going to do, all of these will proceed by induction. So all So with induction, you start, we're going to let A be an n by n matrix. So we'll start with n equals 1. And let's see what we have. So for that case, the matrix A looks like just a single entry, A11. Then the determinant of A is simply whatever that thing is. So now let's go through the things that we did. One, multiplying a multiple of one row to another row. Well, there's only one row to work with, so nothing to do here. But for number 2, what do we have? Swap two rows? Nothing to do here either. And the only thing that we can really do is part 3, and that's where we take and look at the determinant of the single element alpha A11, that's where we multiplied the row by alpha, that equals alpha times A11, which is, of course, alpha times the determinant of A11. Now, that's not enough for the induction. That would work for number 3. It would be okay to start the induction that way. But since we weren't able to do anything with 1 and 2, we need to work at n equals 2 and do something with it. So n equals 2. And I'll show all these things to be true for n equals 2, and then we can start the induction process. So for n equals 2, A is going to equal A11, A12, A21, A22. And let's go ahead and do these processes to it. So for part 1, that's where we multiplied one row by something and then added it to a second row. So let's do alpha R1 plus R2. And this will be the matrix B that they're talking about. So I have A11. I'm going to move it all the way over here, A12, because for the second row I'm going to have alpha A11 plus A21. And then I'm going to have alpha A12 plus A22. And let's take a look at the determinant of B. So remember how this works. We do the determinant of a 2 by 2. I take and multiply the 1, 1 with the 2, 2. So it's going to be A11 times alpha A12 plus A22 minus alpha A11 plus A21 times A12. And let's go ahead and multiply everything through and see where we're at. So I will get alpha A11 A12 plus A11 A22 minus alpha A11 A12 minus A21 A12. And let's see, we can see that this cancels. And we're left with A11 A22 minus A21 A12. And if you look back up at A, that is exactly the determinant of A. So that takes care of the beginning of the induction hypothesis for part 1. Now we'll move on to part 2 where we swap rows. Oh, before I do that though, leave it to you to show the same thing happens when we do alpha R2 plus R1. So if I take a multiple of the second row and add it to the first, you're still going to get the same determinant. So I'm going to leave that to you. Move on to the second one. This is where we swap 2 rows. So we'll take R1 and swap it with R2. So in this case, B then is A21, A22, A11, A12. And let's take the determinant of that. So when I do my cross multiplying, I'll get A21, A12 minus A11, A22. And if you look, if I pull out a negative here, I'll get A11, A22 minus A21, A12. And that is the negative of the determinant of A. So far, so good. And now for the last ones where we multiply just one row. So I'll do alpha R1 to produce my matrix B. So I'll get an alpha A11 alpha A12, A21, A22. Once again, we'll do the cross multiplying to get the determinant of B. So I'll have alpha A11 times A22 minus A21 times alpha A12. Let me pull out the alpha that is common to both pieces. And you can see that that is alpha times the determinant of A. So this is part one of our induction hypothesis. We've proven it for n equals 2, n equals 1 and n equals 2, but n equals 1 where we could. Now let's go ahead and move on to the induction. Now, assume all parts 1, 2, and 3 hold for n equals k. That is, we assume the 3 statements are true for k by k matrices. Let n equals k plus 1 and A k plus 1 by k plus 1 matrix. Throughout, whenever I write Mij, this is the matrix M, but with the ith row and jth column removed. And you remember, when you do the determinant, you mark off the column that it's in and the row that it's in, and you concentrate on the entries that are left after taking out that row and that column. Fortunately, if we are starting with a matrix whose size is k plus 1 by k plus 1, removing a row and removing a column will make the matrix into a k by k matrix, and we're already making certain assumptions about the truth of k by k matrices. So for part one, we add something from one row to another row. So we're going to do alpha Ri plus Rj. So let's take a look at what B is equal to then. I'll make it extra big. I don't think I need to make it as big as I'm going to, but I'm going to anyways. So we'll be going along fine until I get to row J. I will have alpha AI1 plus AJ1 and this ends here A1N. So I've really only affected one row in this. So you can see it's exactly the same as the matrix A, except my row J is going to look different than this. Now, for determinant B, expand along a row not affected by this row replacement. I really think that I don't need to worry about row J. So what we're going to deal with then is we'll expand along another row. And notice there's two rows that are affected here. I and J are affected. However, my matrix, because I've proven things true for 2 by 2, this matrix is at least 3 by 3. That means I will have a third row to play with where I'm not going to affect the row replacement, and I won't mess around with rows I and J at all. So we'll expand determinant B about row L. And row L will not equal J. I don't know that I need to bother with it being involved with row I, because row I is really unaffected. So I probably can, L can be row I. I'm sure I'm not going to run into a problem. All right, well, let's take a look at the determinant of B. And to save myself some ink, I guess, I'm going to use the absolute value symbols for that. So here, as we expand along this row, here's what we get. That, of course, takes care of the negative at the beginning. So as you recall, that's our formula for the determinant of a matrix. Goes like that. Now, since so if I take any one of these matrices, B, L, P, I don't really care what the P is. If I take any of them, the size, each of these is K by K. So we can use our induction hypothesis to get the determinant of BLP equals the determinant of ALP. That's by the induction hypothesis, the determinant of, for n equals 2, and what we're assuming was the determinant was unchanged. Now, with that in mind, then I can go back up here to this and replace these BL somethings with AL somethings. So I'll get the absolute, well, the determinant of B is -1 to the L plus 1, AL1 times the determinant of AL1 plus -1 to the L plus 2, AL2 times the determinant of AL2 plus ... plus -1 to the L plus n, ALN times the determinant ALN. Well, of course, all of those involve A, so this is actually equal to the determinant of A. And that takes care of one of 3 things that we need to do. All right, number 2 was the row swap. So I think what I'm going to do is take row I and swap it with row J. So B then will look like the following. Give myself plenty of space here. I'll have an A11 and I'll come down to, what I want to do is do AI minus 1, 1, and then I will have an AJ1, and then I'll have an AI plus 1, 1. Just to be on the safe side, I want to make sure that I have all of those things. Keep going. I may need to make my matrix even bigger. When I get to row J, before I get to J, I'll have AJ minus 1, 1, and then I'll have AJ plus 1, 1, and in between, I will have AI1, and then AJ plus 1, 1, and the rest will be the same. So then we will get down to AN1. Now let me go ahead and make this thing much bigger so I can encapsulate everything in it. And then just to get the feel for it, A12, dot, dot, dot. Then we'll have AI minus 1, 2, AJ2, AI plus 1, 2, dot, 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 AJ minus 1, 2, AI2, and then AJ plus 1, 2. I see I made a mistake here. That should be a 1 there. And of course, we'll go ahead and go on and on and on. And throughout, I've used a comma when I think it will be useful to separate the indices. All right, so we are going to do the same thing as before. I'm going to operate on a row that is not involved in these swappings. So I've dealt with rows I and J. They've been swapped, so I'll pick a row that's not equal to either one of them. So let L not equal I or J, so L equals neither one of them. Then if I take a look at the determinant of B, I'll expand along row L. All right, and let's see what we have. Same formula as before. As before, BLP is of size K by K. So the determinant of BLP equals the negative of the determinant of ALP by the induction hypothesis. So let me go ahead and do the B again. Now I can go ahead and change the determinants with the B's and turn them into A's. And I made a mistake though, didn't I? Let me do it real soft here. The hypothesis for these was that we were equal to the negative of that. Of course, then I can bring that negative out in front of the whole thing. And don't forget my end cap. And of course, that is equal to -1 times the determinant of A. For the last one, let's do alpha R, alpha times rho I. And then we'll expand determinant B along row L, which does not equal I. So once again, I probably could have done this all in one shot, but I do want you to get comfortable with the summation, or at least how the basic format for the structure of the determinant and what it looks like. So along row L, this is what I get. And you probably can guess this one, since each BLP is of size K by K, we have that the determinant of these things equals alpha times the determinant of ALP. And so when we run the equation again, I'll get an alpha inside of there. Of course, you can factor out an alpha from everything, and you'll find that you'll get alpha times the determinant of A. But let's do some examples to illustrate these properties. So let's start with this determinant. I have 3, 3, -3, 3, 4, -4, 2, -3, -5. Now what I can do is pull out a factor from exactly one row, like so. I found it useful to have the one up in this left corner, so let's go ahead and clean up a little bit. So I'll do -3R1 plus R2, and you only need to go as far as you have to go until you see what the result is going to be. So you may not have, all I'm saying is you may not have to run this all the way until you get a row reduced matrix. So I did -3R1 plus R2, so I'll have a 1 in this spot. 3 minus 4 is -1. -2R1 plus R3. So -2, that'll make that a -5. And then we have 2 minus 5 will be -3. And I'm almost where I want to be here. I'm going to take out this -5. Remember, you can just multiply by the diagonal once you get it into a diagonal form, which is the same as an echelon form for this particular matrix. So we'll do 5R2 plus R3. Let's see here. -5 minus 3 is -8. And then to finish it off, all we have to do is we have the 3 here, and then we just multiply by the diagonal element. So I have times 1 times 1 times -8, which equals -24. I guess using the absolute value symbols, people are surprised when they get a negative answer. But just remember, in this class, the absolute value symbols actually mean the determinant. Let's do another one. What we got here is a 4x4. Okay, let me clean out the first column. All right, let's see what we have then. -6 plus 7, that'll be a 1 there also. And then we have -4 plus 6 will be a 2. And then we have 8 minus 3 will be a 5. Oh, I almost saw that I had the same 2 rows, but I guess I do not. A little bit of difference there. Okay, and then finally, let me take out this 3 here. So I'll do 3R1 plus R4. 9 minus 10 will be -1. And then I'll have 6 minus 7 will be -1. And then I'll have -12 plus 2 will be -10. And that, now remember, none of those change the value of the matrix. So what I'll go ahead and do now is use this one right here to wipe out the things below it. I'm just shooting for a diagonal matrix. Upper triangular, in fact. Let's see then. We would do -R2 plus R3, and then we would do R2 plus R4. Oh, good. Let's see, 10. I'll have a 10 here. And then when I wipe out the 4th row, see what I did. 2 minus 1 will be a 1. -5 minus 10 will be -15. And I can finish it off. It's almost where I want it. I want to swap these last 2 rows. So I'll do R3 swapped with R4. So don't forget there's a negative now in front of the matrix. Well, in front of the determinant. And let's go ahead and calculate it. Now that I've got it in the upper triangular form, I have a negative. And then the product of the diagonal elements, 1 times 1 times 1 times 10. Now a little bit of practice with the theory, even though that was practice, but let's just say I give you an unknown, A, B, C, D, E, F, G, H, I, and all you know is that determinant is equal to 7. So if you have A, B, C, 5D, 5E, 5F, G, H, I, that equals 5, because you multiplied one row by 5, so it's 5 times the determinant. That's 35. Moving on. Suppose we have D, E, F, A, B, C, G, H, I. Well, here you've swapped two rows. In fact, you've swapped rows 1 and 2. I'll input R1 has been swapped with R2. So we get the negative of whatever the determinant was before. Here I probably should have just said 5R2 so you can keep track of what I'm doing. And then of course we're going to do one more. That'll be the row replacement. A, B, C. I'm going to need some space. D plus 3G, E plus 3H, F plus 3I, G, H, I. And notice this is a row replacement thing. I took 3R3 plus R2. That doesn't affect the determinant at all. So we get the same as what we started with. Another theorem. If A is an n by n matrix, determinant A equals determinant A transpose. Proof. For n equals 1, A equals, as before, A11. A transpose equals exactly the same thing. And so the determinant of A does equal the determinant of A transpose in that case. If I do n equals 2, A equals A11, A12, A21, A22. The determinant of A is A11, A22 minus A21, A12. Now if I look at its transpose, remember the diagonal elements are unchanged. It's the other elements that will change. So for this, I'll get A11, A22 minus A12, A21, and that's exactly the same as the determinant of A. So for n equals 2, we have determinant A equals the determinant of A transpose. Assume the theorem is true for K by K matrices. And let A be a K plus 1 by K plus 1 matrix. So we have the determinant of A. We'll go it doesn't really matter. We can go along row I or along row whatever. I think I am going to go just along row 1 is good enough. So there is expansion of the determinant along row 1, and we know that this equals the following. Because each of those matrices is only k by k, so we can use the induction hypothesis for this. This is, I guess we could put by induction hypothesis. However, this here is the determinant of A transpose. Because if you look at these here, let me put a 1, 1 in here. If you look at this, when you're considering the transpose, this is along the first column of the transpose. So this is expanded another theorem. A square matrix A is invertible if and only if its determinant is not equal to 0. The proof. Let U be an echelon form of A. So what are the possibilities that this can look like? Well, we could have U equals, I don't know how these to put. Let's see, we could have, let's see, a block. Say that's A11, and we have a block, A22. But you could skip some blocks, some columns. That could happen. Who knows where these things could be, but you could end up at A and N. And you may or may not have all of these diagonal entries. Depending on if A is invertible, then you will have complete upper triangular matrix, and you will have all the pivots on the diagonal. Of course, when I call these, I'm not this after it is in echelon form. These are not necessarily A11. I probably should say that this is entry 11 instead, because we don't know what the actual numbers will be. We don't know that they will be A's, the original A's to begin with at all. I know we'll have zeros underneath it there and stars above. So now, if A is invertible, it has n pivots. That means we're going to have the diagonal structure that I'm looking for. And the determinant of U will equal block 1, 1 times block 2, 2 times block n, n. And in fact, because of the way that theorem was structured, I can do this. A is invertible and put inside of here if and only if. So that takes care of this all in one swoop. Now, another form let's say some of these may not be a complete diagonal. So for instance, maybe one of these here is like It should be in, see how this would be, the next one should be 2, 2, but maybe it's not. Maybe it's an I, and then the other spot is like I plus K or something. So you have like a gap of K spaces or whatever, and it goes on, who knows. Well, in this case, the determinant of U is obviously going to be 0 because you have less than n pivots in that case. We don't have a pivot in every single column. We'd be skipping columns. In other words, we'd have free variables, whatever you want to call it. And the determinant, A is invertible if and only if it has n pivots. And so in this case here, we have less than n pivots. A inverse doesn't exist. Okay, so what I've proved now is that echelon determinant is not equal to 0 if and only if A is invertible. So this is what we have so far. This is exactly what I have so far. I have not proven it for the determinant of A, though. So recall this. Recall these elementary matrices. So the determinant of A will equal the determinant of EP dot 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 E1 times U. Now, depending on what EP is, now it could be the same as the determinant of EP minus 1 all the way down if that first thing was a row replacement. Remember, the determinant's the same if you take the multiple of one row and add it to a second row. We could have the negative of EP minus 1 dot 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 E1U if EP was a row swap. A row replacement matrix is better. And what was the other one? Alpha times EP minus 1 dot 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 E1U if EP was a multiply one row by alpha matrix. So we've already handled those before anyways. Then let's see what we have. Then when I look at the determinant of A, as I go down, I don't know what's going to happen in the first thing. I could have a -1, I may not. So let me put -1 to some power, alpha to some other power. You know, this K and T could be 0, so these could do nothing. But so in the first thing, I either multiplied by a negative or multiplied by a power of alpha or did nothing. So I could do this again, and I really wouldn't have to adjust these because these K's and T's will be ready for any kind of a thing. So even if the next one adds to an alpha, my T will just grow by 1. It really doesn't matter. You know, now it'll be, if it was an alpha, this would be, if it was alpha to the 5 before, now it'll be alpha to the 6th. Whatever. My T just changed. That's all that happened. Well, you can see I can keep doing this until I get to this. Of course, this is the determinant of A. And we already know what happens. This thing here, alpha, I'll assume that alpha is not 0, although you can possibly do that. If alpha is 0, it just zeroes out everything. Both determinants will be 0 anyways. But nonetheless, U then so when it comes to invertibility, U tells us what's going to happen. So this will equal 0. That'll equal 0 if A is not invertible because U is not invertible. And does not equal 0 if A is invertible. Let's see here, we'll do a 3 by 3 for my example. 2, negative 6, 5, 3, negative 9, 6. This does equal 0 because the columns are not linearly independent. Remember, the columns have to be linearly independent for the matrix to be invertible. So if you take a look at these guys right here, this column right here is negative 3 times the first column. So that's negative 3 times column 1. So you know that these 3 columns are not linearly independent. The matrix is not invertible. Therefore, its determinant is equal to 0. Another theorem. Let A, B be n by n matrices. Then, the determinant of A times B is the determinant of A times the determinant of B. Case 1. A is not invertible. Then AB is not invertible either. Why? Because if AB were invertible, then it would have a right inverse C. So we'd have AB times C would be the identity matrix. However, we could reassociate here. This would imply that A has a right inverse. And if A had a right inverse, it would imply that A is invertible. We're not doing any of that stuff. So we know that AB is not invertible. All this stuff can't happen. So we do know this. In this case, then, 0 is equal to the determinant of AB because the determinant of AB is 0 because it's not invertible. Well, this equals the determinant of A times the determinant of B. Even though I don't know what the determinant of B is, I know that A is not invertible, so its determinant is 0. So in this case, I have the determinant of AB equals the determinant of A times the determinant of B. Now that was just one case. Now let's move on to the case where A is invertible. So then A will equal EP times ... up to E1. EI is an elementary matrix. Let me say each EI is an elementary matrix. And we'll play the same game as we did before. Now, each of those elementary matrices, we know we can pull them out one at a time. We've done this process a few times now. So according to the work we've done before, I can do this again and again and again. Keep going until I get all the way down to B. Now go ahead and work in reverse to gather up just the E's. And we know that that stuff, the EP to E1 is equal to A. And we got what we want in that case as well. If A is invertible, then the determinant of A inverse equals 1 over the determinant of A. Here's proof. This is a really simple one here. We know that 1 is the determinant of the identity matrix. Of course, we can write this as A times A inverse. A is invertible. I can now break this up. And then I can divide by whichever one I want. I can do that since the determinant of A is not equal to 0. Another example. Suppose you multiply an entire matrix, not just a row, but an entire matrix by an R value. Whatever R is, I don't know, but I'll have RA11, RA1N, R-A-N-N A-N-1. All right, now I can start pulling R's, though, out of a row. So I can pull an R out, and I'll be left with A11, A1N, but I'll still have R times the second row. But I can play this game again. Now I can pull an R out of the second row. And I can keep going like this. I can pull an R out of the third row, then a fourth row, then all the way until the end. And so what you're going to get then, after you pull all these R's out, is you'll get R to the N times A11, A-N-1, A1N, A-N-N. That equals R to the N times the determinant of A.